Hey friends, welcome to the YouTube channel all about electronics. So in the previous video, we have seen that how to perform the binary division. So in this video, let us see how to design the logic circuit which can actually perform this binary division. So here, the circuit which we are going to design is purely combinational circuit. And at the end of the video, I will also show you the simulation results for the designed circuit. So in the previous video, we have already seen the steps for performing the binary division. So this binary division is basically a repetitive subtraction. So just to quickly revise, here I am taking the same example which we have covered earlier. So in the division, what we are doing? First we are comparing the divisor with the selected bits of the dividend. So if the divisor is less than the selected bits of the dividend, then we subtract the divisor from the selected bits. And in the quotient we used to write 1. And then in the result, we append the next bit of the dividend and shift the divisor to the right by a 1 bit. And then we repeat the same procedure. But on the other hand, if the divisor is less than the selected bits of the dividend, then we do not perform the subtraction. And in the quotient, we used to write 0. And then we move to the next step, that is to append the next bit of the dividend. And then we perform the right shift operation on the divisor. So once again, the same procedure continues until we go through all the bits of the dividend. So basically, this binary division involves the three basic operations, that is compare, shift and the subtraction. So here, we can combine the compare and the subtract operation just using the subtraction. So in the subtraction, if the first number is greater than the second number, then the result of the subtraction will be positive. Or in other words, we won't get any borrow at the output. For example, if we subtract this 111 from 1100, then the result after the subtraction will be positive. And hence, there is no borrow at the output. But if the first number is less than the second number, then we will get the borrow after the subtraction. For example, if we subtract this 111 from 110, then this will be the result after the subtraction. And as you can see, we are getting the borrow at the output. So here, since the borrow is equal to 1, so we know that the result is negative. So if there is any borrow after the subtraction, then our subtraction is invalid. And simply, we need to restore the original value. But if there is no borrow, then our subtraction is correct. And in that case, there is no need for restoring the earlier value. So that is how we can combine the compare and the subtract operation. Moreover, from this borrow bit, we will also get the quotient bits for the each iteration. So if there is no borrow, then our quotient bit is equal to 1. And if there is any borrow, then our quotient bit will be equal to 0. So very soon we will see that how to implement that. But here, using the subtractor circuit, we can easily perform the subtraction. And here, a block of 4-bit subtractor is shown. So from this borrow output, we can decide the quotient bits. And we will also get to know whether we need to perform the restoration or not. So for that over here, we also need a control circuit which can perform this task. So basically, this entire block will perform the comparison and the subtraction. So now, let us go one step further and let us see how to implement it. So in the earlier videos of the adder and the subtractor, we have already seen that how the adder circuit can be used as a subtractor. So basically we have seen that during the addition, if we take the 2's complement of one number, then that is equivalent of the subtraction. So for example, if we want to perform the 4-bit subtraction using the full adders, then here one number is inverted. So basically that is equivalent of taking the 1's complement of that number. So in the 1's complement number, if we add the 1, then we will get the equivalent 2's complement number. So here, this 1 is added using the carry input. So for example, if we want to perform the 12 minus 7, then we will take the 2's complement of the 7. And then we will perform the addition. So here, if we perform the addition, then the result will be equal to 10101. So basically over here, we will get the carry bit. And we can use this carry as our quotient bit. So in our division, when the subtraction is possible, then the result of the subtraction will be positive. And in that case, the quotient bit is equal to 1. So here we can directly use this carry bit as our quotient bit. On the other hand, if the one number is less than the other number, then the result of the subtraction will be negative. For example, if we perform this 10 minus 12, then first we will take the 2's complement of this 12, that is equal to 0, 1, 0, 0. And then if we perform the addition, then the result is equal to 1, 1, 1, 0. So as you can see, there is no carry at the output. So from that we know that in this case the result is negative, and the same carry bit can be used for the quotient. That means here, suppose we are performing the 4-bit subtraction, then this C4 bit can be used as a quotient bit. So now in this circuit, we also need to add another circuit which can restore the original number if the value of the subtraction is negative. And for that, we can use the multiplexer. So as you can see, for the restoration, with each full adder, one 2x1 multiplexer is used. So here, this I0 is connected to the A input, while this I1 is connected to the A minus B input. And this selection input is connected to the carry output of the last full adder in that particular row. So for example, if we have a 4-bit subtractor, then this C4 will get connected to the selection line of the each multiplexer. So this one unit of the full adder and the multiplexer will act as the one processing unit or the processing block. And if we combine 4 such blocks, then we can perform the 4-bit subtraction along with the restore operation. So as you can see over here, the carry output of the last block is given as a selection input for the each multiplexer. So if the carry is equal to 1, then the output of this block will be equal to A minus B. But if the carry is equal to 0, then the output will be equal to A. So in this way, we can perform the subtraction and the restore operation. Now along with the subtract and the restore operation, we also need to perform the shift operation. So typically in the sequential circuits, the shift operation can be performed using the shift registers. But here, since we are designing a combinational circuit, so we will achieve this shift operation by properly arranging these processing units. So here, this is the combinational divider which will perform the 4-bit by 2-bit division. That means here, the divisor is of 2 bits while the dividend is of 4 bits. That means here, these D3, D2, D1 and D0 are the 4 bits of the dividend, while the small d1 and the small d0 are the 2 bits of the divisor. And of course, since our dividend is of 4 bits, so the maximum bits in the quotient will be equal to 4. That means here, this Q3 to Q0 represents the quotient bits, and this R2 to R0 represents the 3 bits of the remainder. So here, this each stage or the each row represents the one iteration of the division. So when the dividend is of 4 bits, then at the most, we will have 4 iterations. And therefore over here, the circuit consists of 4 rows. So as you can see, these D1 and D0 inputs are connected to the processing blocks of the each row. And they are connected in a such a way that in each stage or in each row, they are getting right shifted by a 1-bit position. So here, depending on the final carry in the each row, here the each processing block performs either subtraction or the restore operation. And for that, as you can see, the final carry in the each row is connected to the selection input of the each multiplexer. And like I said earlier, here this each processing block consists of this full adder and the multiplexer. So now, let us understand the working of this circuit by taking one example. So let's say we want to divide this 1010 by 11. That means here, our divisor is equal to 11 while the dividend is equal to 1010. That means here, this D3, D2, D1 and D0 are 1010, while this small d1 and d0 is equal to 11. That means here, the inputs at all these positions will be equal to 11. So now, what we will do? We will perform the same division on the right side using the restore method, and on the left side we will see that how the circuit performs the same operation. So as you know, in this restore algorithm, first we will compare the divisor with the first bit of the dividend. So basically, we will subtract this 11 from the 01. And here, since the 0 1 is less than 1 1, so the result after the subtraction will be negative. Or in other words, we will get the borrow output. And since we are getting the borrow output, so we will restore the original bits. And therefore in the quotient we will write 0. So the same thing also happens in the first stage of this circuit. So like I said, here the small d1 and the d0 is equal to 1 1, while this d3 bit is equal to 1. That means here these two processing units will subtract the 1 1 from 0 1, or in the 2's complement form, that is equivalent of 0 1 plus 0 1, and that is equal to 1 0. So as you can see, there is no carry after the subtraction. That means here this quotient bit q3 will be equal to 0, and since the final carry is equal to 0, so the multiplexer will perform the restore operation and it will restore the 0 1 at the output. That means the input to the next stage is equal to 1, and here this d2 input is equal to 0. That means in the next stage if you see, then the 1 input is equal to 0 1 0, while if you see the bits of the divisor, then that is equal to 1 1. Now on the right hand side in the actual division, if we see the second iteration, then in the second iteration we will bring the next bit of the dividend, and then we will right shift the divisor by a 1 bit, and once again we will perform the subtraction. So once again, since the 1 0 is less than 1 1, so after the subtraction we will get the borrow, and since we are getting the borrow, so in the quotient we will write 0, and once again we will restore the original bits. So the same thing will also happen in the second stage of this circuit. So as we have seen, here the one number is equal to 1 0, while the divisor is equal to 1 1. That means here these two blocks will perform the 1 0 minus 1 1, or in the 2's complement form, that is equivalent to 1 0 plus 0 1, and that is equal to 1 1. That means here there is a no carry after the subtraction, and therefore the quotient bit q2 will be equal to 0. And since it is 0, so multiplexer will also perform the restore operation. That means now the multiplexer will restore the 1 0 at the output, that is this value, and now this d1 is equal to 1. So now the one number to the processing block is equal to 101, and as you know, here the divisor is equal to 1 1. That means the second number is equal to 011. So now this 011 will subtracted from the 101. So on the right hand side if you see, then the result of the subtraction is positive. So in the quotient we will write 1, and then we will append the next bit of the dividend. So the same thing will also happen in the third stage. So here this 101 minus 011 is equivalent to 101 plus 101, and that is equal to 1010. So as you can see, here we will have a carry after the subtraction. That means here this q1 bit will be equal to 1, and since the quotient is equal to 1, so the result of this block will be equal to a minus b, that is equal to 0 1 0. So here this will be the 0, while these two outputs will be equal to 1 0, and as you know, the small d1 and d0 is equal to 1 1, and now this d0 bit is equal to 0. That means here the one number is equal to 100, but the second number is equal to 011. So on the right hand side in our division process, if we perform the same subtraction, then we will get 01, and since there is a no borrow, so in the quotient we will write 1. So here this 01 is the remainder, while this 011 is our quotient, and the same thing also happens in the final stage. So here this 100 minus 011 is equivalent to this 100 plus 101, and that is equal to 1001. So as you can see, here this carry output is equal to 1. That means here this q0 output will be equal to 1, and since it is equal to 1, so the output of this last block will be equal to a minus b, or in this case that is equal to 0 0 1. That means here the remainder is equal to 0 0 1, and if you see the quotient bits, then that is equal to 0 0 1 1. So in this way this circuit performs the binary division. So now let me show you the same thing in the simulation. So as you can see, here each block consists of the full adder and the multiplexer, and here the divisor bits are inverted only once. So here these 4 bits represents the quotient bits, while these 2 bits represents the divisor bits, and here the 4 bits of the dividend are applied through this switch. And as you can see, here these 3 bits represents the remainder bits. So here, just to see the result of the remainder, these 3 outputs are connected over here. So now let me just run the simulation and let me show you the output. So initially this B1 B0 or the divisor bits are set as 0 1, while the dividend bits are set as 1 0 0 1. That means here the divisor is equal to 0 1, but the dividend is equal to 1 0 0 1. So in that case, as you can see, the quotient is also equal to 1 0 0 1, while the remainder is equal to 0. So now let me just make this divisor is equal to 1 1. So now our divisor is equal to 1 1, while the dividend is still equal to 1 0 0 1. So as you can see, now the quotient is equal to 1 1, while the remainder is still equal to 0. So in this way we are getting the correct result. So now the dividend is set to 1 0 1 1. So in that case, now this circuit should perform 1 0 1 1 by 1 1, that is 11 divided by 3. So in that case, as you can see, now the quotient is equal to 1 1, that is 3 in the decimal, and the remainder is equal to 1 0. So in the decimal that is equal to 2. So once again we are getting the correct result. And now let me just change the dividend to the 1 1 1 1. That means now our dividend is equal to 15, while the divisor is equal to 3. So in that case our quotient should be equal to 5. So as you can see over here, the quotient is equal to 101. So in the decimal that is equal to 5, and here the remainder is equal to 0. So now if I just change the divisor to 10, then this circuit should perform the 15 divided by 2. So in that case, as you know, the quotient should be equal to 7, while the remainder should be equal to 1. So as you can see over here, now the quotient is equal to 1 1, while the remainder is equal to 1. So in this way, this circuit performs the 4-bit by 2-bit division. So in this circuit, since our dividend is of 4 bits, so we will have 4 rows. That means here, the number of rows in the array is equal to the number of bits in the dividend. Now the second question is, in each row, how many processing units we need to add? Now since the divisor is of 2 bits, so in the first 2 stages, we will have only 2 units. And after that, in each stage, we will have 1 more unit. That means as you can see, in the last 2 stages, we will have 3 units. So in this way, we can design a divider circuit which can perform the 4-bit by 2-bit division. So similarly, this is the 5-bit by 3-bit divider circuit. So here, the dividend is of 5 bits. And since it is of 5 bits, so we will have total 5 rows. Moreover, since the divisor is of 3 bits, so the first 3 stages or the first 3 rows will have only 3 units. And then after, in the next 2 rows, we will have 1 more unit. That means if you see the 4th and the 5th row, then it will have 4 units. And as you can see, in these additional units, the input is equal to 0. So in this way, we can design this divider circuit. So this type of array divider are also known as the fast divider. But as you can see, as the number of bits in the division increases, then the required number of processing blocks will also increase exponentially. So typically for the division, the sequential division circuits are used. And in the future videos, we will also cover that. But I hope in this video, you understood how to design a logic circuit or the combinational circuit which can perform the binary division. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.